In addition to the Burke Nanotechnology Center and STEM learning laboratories in Purdue University's Discovery Park, CISTAR will access an additional 5,000 square feet of laboratory space equipped for catalyst research. From automated units for kinetic measurements to operando plug flow reactors that connect researchers to the advanced photon source at Argonne National Laboratory. State-of-the-art reactor cells for infrared, UV vis, and synchrotron equipment. And advanced analytical instruments will enable elemental analysis of solid materials. We can synthesize and prepare solid and zeolite catalysts in the Materials Synthesis Laboratory and use powder X-ray diffraction to obtain data up to 1,500 degrees Celsius. An ultra-high vacuum, high-pressure single crystal reactor will support surface science synthesis and characterization. We will use specialized facilities at Burke Nanotechnology Center to measure the chemical state of the catalyst before and after reaction without exposure to air, and to image the catalyst at atomic resolution under temperature and dynamic gas composition. For our systems-level test beds, Zytel and Zeton units donated by BP will allow product testing at industrial conditions. In addition, Purdue is the top-ranked university in the nation for supercomputing with 1,570 teraflops. Advanced computation needs of Purdue researchers will be met through a Beowulf-class supercomputer with 11,520 compute cores. The Advanced Materials Laboratory at the University of New Mexico includes instrumentation with advanced capabilities for CISTAR light hydrocarbon research, such as high-resolution Raman chemical mapping with fast throughput and sensitivity, characterization of nanostructures ranging from 1 to 125 nanometers. An analytical X-ray photoemission spectrometer provides high sensitivity, high spectral resolution, mapping, and imaging of high-temperature catalytic reactions. With our micro-diffraction system, CISTAR researchers can obtain conventional diffraction patterns from volumes of materials normally considered too small for conventional powder diffraction. And a multi-purpose diffractometer addresses the advanced thin-film, low-volume analytics. In the Brinker lab, a gas and vapor sorption analyzer will allow us to determine micro and mesoporosity of candidate membrane materials. And we will have rapid prototyping of candidate high-flux membrane support architectures for CISTAR membrane research. The Catalysis Laboratory for the Dautier Group will have a new laboratory space beginning October 2016 for the synthesis of catalytic materials. The laboratory will house a suite of advanced instrumentation, including those capable of running high-resolution environmental scanning electron microscope and fabricating nanopatterns and devices using both etching and deposition. For our materials synthesis projects, we will be able to study soft samples, such as liquid, and will have in situ observation of nanoparticles in various environments. Multiple reactors in our laboratory will allow CISTAR to determine reactants and products from the reforming of methanol, the conversion of propane, and the hydrogenation of acetylene at various temperatures with flow through a catalyst bed. Our treatment furnaces will allow us to synthesize catalytic materials. The Clean Catalysis, or CleanCat Core facility at Northwestern University is believed to be the only user-facility gas phase flow reactor in the United States. On the 4-station CleanCat testing platform, reactors can perform all of the targeted dehydrogenation, hydrogenation, oligomerization, and oxidation reactions targeted by CISTAR. The entire system was custom designed for Northwestern's Catalysis Center. Our Micromeritics 3-flex instrument will be used for measuring exposed surface areas of materials through physisorption of nitrogen or vapors. As with the CleanCat flow reactor stations, high-pressure reactors are fed by a gas manifold. CISTAR investigators can reserve time on reactors to rapidly test new catalyst formulations, especially for new reactions where permanent infrastructure may not yet be in place. The AMI 200 station allows the analysis of catalyst properties by temperature-programmed reduction or oxidation or chemisorption of gases. Gas manifolds and tank farms allow reliable and safe operation. This shared equipment, just like all of the CleanCat resources, can be reserved by CISTAR researchers and is maintained by trained staff. The University of Notre Dame has extensive laboratory capabilities for the design and synthesis of novel polymers that are structurally and chemically functional for high-performance gas separation membrane materials. We are equipped with versatile synthetic techniques and chemical modification tools. Our established film solution casting techniques allow the production of large-sized and defect-free thin films in a scalable film casting process. Custom-built pure gas permeations systems will enable accurate and reliable separation performance tests for 6 light gases that cover all separation needs in chemical industry, from air separation, carbon capture, natural gas purification, and hydrogen purification. CISTAR researchers will have access to high-pressure flow reactors for liquid and gas phase operation. Our gas phase flow reactor is designed for lower pressure and high temperatures to study dehydrogenation of alkanes and the dry reforming of methane. It operates in the presence of a plasma and is connected directly to a gas chromatograph for product analysis. Custom-built Schlenk lines are used to synthesize air and moisture-sensitive catalysts. The tube furnaces are used to synthesize carbides, phosphides, oxides, and reduced metal catalysts. The Hicks lab also has 2 par batch reactors to perform gas-liquid phase reactions for oligomerization reactions. A variety of instruments are available for reaction quantification, as well as catalyst characterization. In addition, Notre Dame's ComCell space offices, which occupy more than 4,000 square feet and can accommodate up to 50 student researchers, provide access to the high-performance computing resources of the Notre Dame Center for Research Computing. Unique facilities at the University of Texas at Austin are among the most advanced in the world and will be available to CISTAR researchers. The James R. Fair Separations Research Program pilot plant is one of the largest multifunctional separations pilot facilities in the world. Each year, the pilot plant generates more than $2 million in research. 4 professional staff members operate this facility, which is available to large and small companies, inventors, and especially graduate and undergraduate students. Large columns allow the development of hydraulic and mass transfer models for improved scale-up and design. And the facilities utilize the most advanced wireless and safety monitoring technologies. The pilot facilities can also be used for liquid extraction studies, as well as emulsified oil recovery experiments using a patented membrane process. With over 25 years of experience in lab-scale Oldershaw distillation technology, the pilot plant can be used to validate computer process simulations and reactive distillation. We will draw on the Fair Separations Research Program pilot plant's strong track record of collaborating with both industry and academia. We will have a unique opportunity to help provide a world-class education that develops the next generation of light hydrocarbon engineers. The University of Texas headquarters for CISTAR will be housed on the 3rd floor of the new Engineering Education and Research Center, or EERC. This new 2-tower complex will open on the Austin campus in 2017 for 21st century engineering research and education activities. Joan Brennecke, the Deputy Director of CISTAR, will be housed in EERC along with an administrative assistant. In addition, she will have 3,800 square feet of laboratory space on the 3rd floor of EERC for conducting research associated with CISTAR. There will also be office space for graduate students and postdocs, as well as conference rooms and meeting space. The EERC is located in close proximity to the Chemical and Petroleum Engineering Building, home of the Chemical Engineering Departmental Offices.